All right, so what do we got here? We've got this one here. So we've got a car that starts from rest on a straight path at the position shown. And we got the velocity of the car is 0.3 t squared. So at t equals 4, let's find the acceleration of the car, the velocity of the car, and the position of the car on the track, okay? So what we've got going on here is we've got distance, we've got velocity, and we've got acceleration. And if we go that away, we use a derivative. And if we go this away, we use an integral, okay? So that's how I think about this. You can go either way. And that's something you want to kind of keep in your mind straight, you know, how you get from one thing to the other. All right? Now, what you got going on here is you've got the velocity, and that's given as 0.3 t squared. So that's where you're starting. So that's the information that you've got. Now, the other thing you want to be looking at is right there. That's some information that you're given too. So, okay, so that's kind of the information that you want to start with. So what you want to do then is start figuring this stuff out. You're looking at t equals 4. So when t equals 4, I think you can figure out that the velocity at 4, just by plugging 4 into that relationship, is 4.8 meters per second. Okay. Just plug 4 in. Easy enough, okay? So any questions on that bit? Okay. All right, now the acceleration then, what you want to look at then is dv dt. That's the fundamental definition of acceleration. Notice that the velocity is given as a function of time. So if you take a time derivative of that, you'll get to the acceleration. So that looks to me like it'll be 0.60 t. So again, when t is 4, what you're going to have then is the acceleration at a time of 4 will be 0.6 times 4, it'll be 2.4. That's one thing I would notice there. Now the other thing that I'd notice is that I've got a at 0.6 times whatever the time is. So it looks to me like the acceleration is changing with time. Okay, so I do have to use calculus on this, so I can identify that. So what I've done here, I've got the acceleration of the car and the velocity. I need the position. That's the last thing I need. Now that's, okay, and I don't have that readily available. It's not like I can just plug in a t and get that. So what I'm going to have to look at then are the available ways I have to get that, and I'm in variable acceleration. So what I've got then are these different relationships. I got ds dt is equal to v, I've got a is dv dt, and I've got ads is v dv. Okay, those are the three relationships that I can work with. Now, I need to involve s, because that's what I'm after, is displacement, and I've already used this one, so that one's out. Okay, that ain't going to work. Okay, I have the acceleration and velocity as functions of time, not of displacement. So I don't think that one's going to work either. So I think I'm on the one on the left. Okay, and that's my thought process on that I go through. So what I've got is that ds dt is v. Okay, that's what I've got. Okay, so that's what I'd want to be working with there, is the change in displacement with respect to time is equal to the velocity, and I'm given that that's 0.30 t squared, okay, is what I'm given. All right, now and then we just go into that standard technique that you use. If the change in displacement with respect to the change in time is 0.3 t squared, that means that the change in displacement is 0.30 t squared times dt, all right? I can split them up like that. And then that's an instantaneous equality. That the change in displacement over a very, very, very small increment is 0.3 times whatever the square of the time is times the small change in time. All right? Now I want to relate s to t because I want to find out what s is when t is 4. So to do that, I'm going to have to add up all those little increments over a larger span so that instead of having ds and dt, I've got s and t. And the way you add stuff up is with an integral. Okay? So that's the step you want to get to, and your intent on that is to be able to get to a relationship between s and t. Right? That's what we're after. So you all okay with that business there? All right. Now you need limits. Remember, we don't do indefinite integrals here because we pick up the c, and that's really doesn't do us much good. I mean, you know, obviously you can figure the c out, but the way we get that stuff all figured out is we put limits in. So what you're going to have to do now is to find limits that you can put in there. All right. And I think there's a limit right there. See, that's telling us what is happening when the time is 0. So notice we're not starting on a number line at s equals 0. We're starting 8 meters down the line. That's where we're starting when t is 0. So that affects the limits, okay? And again, I'm emphasizing this a lot, but pay attention to it, okay? Because, you know, the starting and stopping points on this integration process is very important, and that's, you define that with limits, all right? So you're going to want to plug those numbers into there, and then you're going to want to run your integral, okay? And so when you integrate ds, of course, you get s, and when you integrate 0.3 t squared, you get 0.10 t cubed. And then we're going to have these lower limits that we got to pop in there. Now the upper limits I like to put in as letters, okay? I always do that. So you're going to have to figure out what to put there and there, okay? And I'm giving you a couple hints on that, okay? And I'll probably give you one more too. All right. So what you're going to end up with here when we run through that process is that s minus 8 is equal to 0.10 t cubed. So the displacement then is 0.10 t cubed plus 8. All right. And as we like to see there, the mathematics kind of backs up our common sense. See, we're starting at a distance of 8. That's where we're starting. That's why we're adding that in, okay? Because we're already 8 meters down the road. Okay. So what we want to do then is plug in t equals 4. So when t equals 4, s is equal to 14.4. Okay. So that's the drill on that one. So do we have any questions on that? Doing all right? Okay. So there you go. All right, we got another calculus one here. It's right there. You've got this particle going down a surface. Now, S is displacement in meters. Now, watch for this, and I've been teaching this stuff a number of years, and there's, these little things that trip people up, and that's one. People see that S, they think it means seconds. It doesn't, okay? S is displacement in meters. So what we have here is the acceleration is 0.12 times the displacement, okay? That's what that first sentence says. All right. Now, the other thing we got going on here is this statement right here. The velocity of the particle is 0.8 meters per second at a displacement of 0. That looks a lot to me like a statement about the limits of integration, okay? So watch out for that. Don't just take an antiderivative. You've got to evaluate the limits of integration. Okay. All right. right, now the other thing here is I've got acceleration as a function of displacement. Again, I've got three relationships that I can use, and they're right on your formula sheet there, you know, when you need them. So if you have variable acceleration, you've got these three relationships. These are the possibilities. All right. Now, when you read through that problem statement, the one thing you'll notice is maybe something you don't notice, and what you don't notice is any mention of time in that paragraph, okay? There's none, okay? So we're not relating any of this stuff to time. We're relating it to distance. You all good with that? That there's no mention of time in there? And so what that means is I can't use time, and if I can't use time, I can't use either of those relationships because they're based on dt. Okay? You just can't take some function in regards to displacement and plug it into a relationship with time. They just don't mix. They don't match. Yeah, question there.
What would be like a real application to where we would relate something to the displacement rather than time?
The most common one was that one I did in class, a spring. Because the spring, you know, if you have let's say a linear spring, which is the most common, an even conical, or not conical, cylindrical wrap on the spring with even spacing, you've got a relationship between force and displacement. So that's the most common example that comes into my mind, where I'm looking for the displacement of the spring, or not the displacement, maybe the velocity of the object as the spring displaces. So that's the most common one that comes into my mind. You know, nothing else is jumping right in there, but that one for sure. Okay. All right. So you're going to take this and you're going to plug it into here. Okay. So that's A. And you can see right away that's going to work out because I got 0.12s and I'm matching it with a ds. And that's another thing about doing these integrals is the variable part has to match the differential part. I've got 0.12s matched up with a ds. I can go ahead and integrate that. See, that's integratable. If I start trying to plug this, I've had people attempt to do this in the past. So they take that and they plug it in here, and then they try and mix it with a dt. You can't integrate 0.12s dt. They don't relate to each other. They're not functionally related, so you can't really work with them. See, so that has to go with a ds if you're going to integrate it. Okay. You okay with that? So what you're going to have here is you're going to have that 0.12s and then times ds, and you're going to equate that to v dv. And see, that's all good because you got variables and differentials. They match. They're on opposite sides of the equation, and then you're going to integrate. And then by integrating, what you do is you take all those little what a mathematician sometimes calls infinitesimals, all these little teeny little pieces that we're looking at, these dv's and these ds's, so we're going to string a bunch of them together into a longer interval that we can then evaluate and turn that back into a variable instead of one of those little ds's and dt's. Okay. So that's what we want to do because we want to relate s to v here. All right, so you're going to integrate that, and you're going to need your lower limits again. And look at that statement that I underlined in green. Okay, that's the one that tells you about the limits, and I want you to be able to do that. So that often shows up on an exam, okay? Because I want to be sure you kind of understand that a little bit, what you're up to, okay? And then the top limits, I always just use letters, because again, I can always plug the numbers in if I need to. But if I want to do more with that relationship, I just don't want to plug a number in there as a limit, because that gets me a number out, not a function. So I like having functions to work with. I can always plug the numbers into the functions. Okay? All right, and then you're going to integrate that thing out. And, these things do get a little messy because that v dv integrates out as v squared over 2. And, like the algebra on this gets a little bit messy, you might say. So you're going to end up with something on the order of, it just depends on how you do it, I ended up with 0.06 s squared equal to v squared over 2 minus 0.32. So that's what I ended up with when I ran through that integral, okay? And I had to do a little bit of algebra on that thing to get that worked out. Okay. and then plug in s equals, you plug in s, and then solve for v, and v comes out to be 2.55 meters per second. Okay. So this is kind of a little bit of a building block that we use, you know, so we can analyze stuff in this class, is being able to handle these calculus kind of relationships. Okay, so there's that technique. You find the proper relationship, you plug the stuff in, then you get the variables and differentials on the proper side of the equations, and you integrate, and you watch your limits. That's kind of the short story on that. So we got any questions on that? Okay, we good? All right, so then we got these ones where things are moving in curves. We're going to use Cartesian coordinates here. Okay, so let's have a look at this one. Do we got any questions on this one? All right.
I was a little confused about X not having a T in it.
Okay, yeah, that means it's constant. So that actually makes it easier, you know. It's more straightforward. All right, so what we got here is we've got the velocity functions given. Okay, so what you're going to want to do here is start with those velocity functions and realize them for what they are. You've got Vx. What that is, another way to write that is dx dt, and that's just equal to 2. And then you got Vy, and that's equal to dy dt, and that's equal to 2t. Okay. So what we got to do now is we want to back off and see we're after a path of this particle. We want to plot it up on the graph. To get to a path, you really need a position function. Okay. So position functions and paths are what really relate well to each other. Okay. So what you want to do then is get to x and to y. So dx is 2 dt, and dy is 2t dt. Okay. So we're doing what we were just doing a minute ago. Okay, this is why I called that a building block for doing other things. Okay, so to get this rectified here, what we want to do is integrate. Okay, that will get us into a variable instead of these little differentials. Okay. Now here's a good example of this thing. You can see where the particle starts. Okay, when t is 0, the particle starts to move from coordinate 0, 4. Okay, so when t is 0, see the construction of that sentence? That's something you want to recognize. When t is this, y is this. Okay, what that does is links them together. They're occurring at the same time. That's the meaning of that. So when t is 0, y is 4. So there's a good example of that limits on the integrals. Okay, it comes right from that sentence. You can also see it right on the graph. All right. And then again, we put letters up here. So y and t, and then you just integrate. So you're going to integrate dy, and you're going to get y, and you're going to integrate 2t, and I think that's t squared, isn't it? So we're going to get y minus 4 is t squared, so y is t squared minus 4. That's what we'll get out of that. I'm screwing something up there, aren't I? Yeah, I'm screwing all sorts of things up. So why don't we kind of just leave it and get this eraser to work, which is a little dicey here. Let's see. Gonna work? There we go. Let's see like that. Okay. Let's just leave it like that for now. Now we can do the same thing on the left, and what we'll get to there is x is 2t. Okay. So now I got x and y basically as functions of t. You might say not quite a function there because I got a t squared, but that's the idea. Now what I want to do here is see, I want a path. And to accomplish that, I got to equate x to y. I don't want to involve t in the relationship. Okay, I want t out of the relationship is what's up here. All right, so to accomplish that, I'm going to solve each of these things for t. So t there is x over 2. And what's t over here? It's square root of y minus 4 is t. There we go. So now I've got what both of those equal in regards to t. Okay, and of course t equals t. So now what I'm able to do is equate x to y. So I got x over 2 is the square root of y minus 4. Okay. So what I had to do, I had to back those off into position functions. Okay. Not velocity like I was given. I want to go back to position. And then once I've got that, I want to solve each of them for t and then equate what's left together. That way I can relate x to y and I can get a path. Okay, and I can go ahead and work through that and get that y is equal to x squared over 4 plus 4. And then I can plot up some points, and that's going to be a parabola that looks something like that. So we're doing all right with that? Okay. So we're good. All right, so on that one, we had basically a velocity function. We worked it back to a position function, then we got a path from that. The next one, you go the other direction with it, okay? So on this one, we've got a path that's given, y equals 3x to the 1/2, and we've got the velocity there of that bar pushing the ball up in the y direction. The velocity in the y direction is a constant 0.27. Okay, so Vy, what that is dy dt, and that's 0.27. Now you can work through that, and what you're going to end up with is a position function for y. It's 0.27 times whatever the time is. And there is a common sense level to that. I mean, the thing starts at 0. It's moving with a constant velocity of 0.27, so y will be 0.27 times the time. You know, distance is rate times time, that kind of thing. Okay. It's all constant there. All right. Now what you want to do is we want to find the x velocity of the ball at a time of t equals 11. And you kind of have to work through positions on this stuff, okay? Because we've got the path. We've got a position for y, we want to get a position for x, and then work our way through velocity. So when you're going from position to path and path to position, sometimes you're given velocities and stuff. You got to work that back to position over to path. You know, you always have to go down through position functions. You just can't jump on a velocity function over to path directly. Okay? So we got to get down there to the position. So what we know is that y is what y also equals is a function of x, 3x to the 1/2. Okay, that's given. So what that means is I can now relate x to t directly, okay? So 3x to the 1/2 is equal to 0.27 times whatever the time is. Because I know that y is 0.27t, and I know that y is also 3x to the 1/2. So 3x to the 1/2 is 0.27t. So what that means is 0.0081, if you work through this, t squared is equal to x. Okay. So I can go ahead and work through the algebra on that. All right, so now I've got x, so I have the position function. So I went from path to position. Again, I just can't go path to velocity. That don't work. I've got to go back to position and go from path to position. Okay. So now I know what x is, so I can just go dx dt, which is vx. And what that is the derivative of that. So that's 0.0162 times t. And then I can plug in when t equals whatever the heck it equals, and it equals 11 Vx, then I can find, and that's 0.178. Okay. Doing all right with that?
Sorry, what did the 0.0162 come from?
I'm just taking a derivative of the 0.0081 t squared, so that's how I'm getting to that, just doing a derivative. Okay. Other questions? Yeah.
Would you recommend simplifying it to 0.0081 instead of using 0.272 divided by 3 squared?
Yeah, I like to get things down, to a basic numerical level. If I don't know, that's how I do things. It's kind of the engineer in me, I want a number. If I'm gonna, one thing, in mathematics and science, they often like things that are based on radicals and pi and stuff like that. But as an engineer, I can't tell a machinist to cut something 4 pi inches long. They're not going to like that. So I think in decimal numbers is how I think. It's just more a matter of outlook, a little different than science and math. Other questions? Okay, this one's a little bit interesting. This has 2 parts. So what you're going to want to do is you're going to want to break this thing up into components. All right. So that's going to be the first step. So we're going to want to know how far out does this thing hit the ground. So when I break it up into components, I get 1.06 I, and I get negative 0.563 J. That's the components of that velocity with the 28-degree angle. All right. Now the next thing that I want to do is part 1 is just a trajectory problem. Okay. I want to get into y. And for me, it's easier on this because everything's moving down. I just called positive down, and that just seemed to work a little bit better for me to do it that way. And what I want to do then is apply an equation, S equals S0 plus V0t plus 1/2 ACt squared. I've got constant acceleration, and that's due to gravity, and that's going down. All right. Okay, now, if I'm calling positive down, my final position is 0.8. My initial position is 0. I've got 0.563 times whatever the time is. And then I've also got the 1/2 times my 9.81 gravity times t squared. My intention here is to solve for t. Okay? So what I'm going to end up with here is a quadratic. 4.905 t squared there, plus 0.563 times t, and then minus 0.8. And that's equal to 0, okay? And what I'll do is I'll run that through a quadratic. And the quadratic formula is negative b plus or minus b squared minus 4ac over 2a. Now, a couple things on that. That's on your formula sheet if you ever need it. Remember, you can't use a programmable calculator on your tests, so you might just be familiar with where that is. But on your homework, of course, you can use whatever the heck you want. So it's not like you got to knock through that by hand on your homework if you don't want to. You got a little function on your calculator. Go ahead and use it. Okay. All right. Now we're going to get a couple roots out of that, of course, like we do, and we're going to get negative. So when we solve for t, then we're going to get negative. Negative 4.654, and we're also going to get a positive t, which is 0.3504. Okay, so I think we want the positive value there. So what I just found out was that if I take that block and slide it down the ramp at 1.2 meters per second, and it's a 28-degree ramp, what I'm going to do, that time for it to hit is going to be 0.35 seconds. Okay. And then to find the distance, then, what I'm going to do is I'm just going to take Vx times the time, because it's all constant. There's no acceleration in the x direction. So I can find my d sub x, I guess. Now that's not a calculus dx, that's d sub x. And that's just my 1.06. times the time, okay? And that'll get me that distance, and it's about 0.371 meters. So that's how far the thing's going to go for this condition. Now, are we good with that? Now, that's how you solve it, okay? If you know the angle and the speed. Now, if you don't know the angle, the solution gets a bit messier, okay? Now, you can do it by hand, but I think what I would tend to do with this is reverse engineer it. I have a nice model on how to work the problem out, okay? I can use this equation to find the time, and once I know the time, I can multiply the time I just found by the distance, by the x velocity, and I can find the distance. Okay, so I have a couple relationships there that will allow me to work through that, two of them. Use that one equation in the y direction to find the time. Once you know the time, multiply it by the x velocity to find the distance. So what I would tend to do on this, instead of trying to plug in the angle as a variable, which will get kind of messy because sine and cosine are some kind of awkward variables to work with, what I would probably do with this is use MATLAB or Scilab or a spreadsheet or something and just program the process that I would use to solve it. So I would program this equation first to solve for a time by inputting an angle. I would leave that as a variable now, but I would follow this exact process, but instead of using those numbers, I would use sine 28 times 1.2 for the y and cosine 28 times 1.2 for the x. Then I would plug in different angles and see how long it takes for those angles, see how long it would take for the block to hit the ground for those angles. Then I would go ahead and take that time and plug it into this relationship. Okay, so what I would tend to do on this thing is create a spreadsheet. So I'm not going to try and solve this thing exactly. What I'm going to try and do here is solve it, create a process to solve it. And then I'm just going to plug numbers into it until I hit what I want to hit as far as my answer. All right, so here's a spreadsheet that I've got set up. So what I have there is I have the height, which is 0.8, because I'm calling positive down. I've got the velocity at 0.2, and then I've got an angle. Now, these things seem to like to work in radians, so I immediately convert the angle into radians. Then what I've got is a column for the x and y velocities based on my angle and my velocity. Okay, So that gets me the x and y velocities. I vectorize the velocity there. Then I take my velocity and I just go ahead, my y velocity, and I just plug it into that s equals s0 plus v0t plus 1/2 ac t squared formula. And that will get me, and I solve it for time using the quadratic equation, that will get me the time. In this case, it would take using a 5-degree angle for that block to hit. Then I take that time and just multiply it by the x velocity, and I get the distance out. Okay? Now, is 5 degrees going to work? What distance am I after? I'm after 0.45. That ain't going to quite work, is it? Is minus 20 degrees going to work? And that's a little short, but I've got it bracketed now, so I know it's somewhere between 5 and 20 degrees, and I just keep throwing angles at it till it hits 0.45, okay? Much simpler solution to me than trying to solve for this directly, okay? This is a numerical solution, which for an engineer is fine, okay? That'll work, all right? So that's how I would solve that. Get it to the nearest degree, okay? All right? Sorry for running over there a bit, so there we go.